Exercise 1.1, question number 3. This is a true or false question. Let's take a look at number 1. The identity relation on A is reflexive. So first of all, you must need to know what is the identity relation. The identity relation on any set A, okay, we define it as I, and it is equal to A comma A. So the elements here are of this type, such that this A belongs to A. Okay, so that means, for example, if A equals 1, and let's take numbers. If A equals 1, 2, 3, then I will be equal to AA, and this is for all A belongs to A. So if A is equal to 1, then according to this 1 is there, then 2 2, and then 3 3. So there will be no other element. All elements are of this form AA. So we close the bracket. This is called the identity relation. Now it says here that the identity relation is reflexive. So is it reflexive? Now we know the condition for reflexivity is what? AA belongs to R for all or for every A belongs to A. Is that true in this case? Yes, it is. You have 1 1, you have 2 2, and you have 3 3. So this is reflexive. So the first answer is true. But then, if you take a look at the next question, it says that every reflexive relation on A is identity relation on A. Now this is an identity relation and it is reflexive, but is the converse true? Is every reflexive relation an identity relation? An identity relation, or are there some reflexive relations that are not identity relations? So if you take here A, the same set, and take R to be, so 1 1, 2 2, 3 3. So one thing you need to know here, when we're talking about reflexive relations, the condition is this: AA belongs to R for all A belongs to A. But it says nothing about the existence of other elements in the set in the relation R. Unlike for identity relation, this I, it directly says that in this set there are only elements of the form AA. So there are no elements of the form AB or different numbers like 2 1 or 2 3. Okay, all numbers in this set are 2 2, 1 1, 3 3 in that form. So it bars the existence of other elements of the form AB where A and B are not the same. But in the case of a reflexive relation, it only says that elements like this AA, they are there, they belong to R. But then it does not bar other elements from being inside of the relation itself. So we can have 1 1, 2 2, 3 3, and another element 1 2. This will still be reflexive even though it is not an identity relation. So it is not an identity relation because it has this element, which is not the form AA. But it is reflexive because it has all these elements AA, they're all in R. So that's why it is reflexive, but it is not an identity relation. So to answer the question, every reflexive relation on A is identity relation, the answer is false. Then, the identity relation on A is symmetric. So let's check this. Is this symmetric? Let me take another page. Identity relation. I equals, let's take the same relation. 1 1 2 2 3 3 for the set A 1 2 3. Is this symmetric? So judging from the picture also we can see, if we draw the diagram, if this is A, this is 1 2 3 1 2 3. If you have your axis of symmetry here, so 1 goes to 1, 2 goes to 2, 3 goes to 3, it is symmetric. Okay, so because in other words, so if we take the element 1 1, if you take this as AB, then what will be BA? So BA will be itself 1 1 and it's there. So if AB is there, B is there. That is true for all elements here. So therefore R here, therefore I here, it is symmetric. So the answer for this number is true. Then number 4, identity relation on A is an equivalence relation. Equivalence relation means a relation that is all three: reflexive, symmetric and transitive. So we've seen that the identity relation is reflexive, we've seen that it is symmetric, so all that remains to be seen now is that it is transitive. Let's see. So regarding transitivity, so A equals first 1 2 3, then I equals 1 1 2 2 and 3 3. Now the condition for transitivity is this: if AB and BC belong to R, then AC must also belong to R. So that's the condition. So we must be very careful with this condition. If this condition is broken, then this relation I will not be transitive. So let's take a look at this question. The question we must ask is this condition broken or not in this case? Okay, so now for example, let me give you an analogy. Suppose there's this rule: if you are in the classroom, then you must not eat. Okay, so this is the rule or the condition. So when can you break this rule? First of all, if you are not in the classroom, then what will happen then? Then you are not able to break this rule, right? Because this rule only applies for students in the classroom. Okay, so if you are not in the classroom, so it doesn't even apply to you, and you can never be a rule breaker. So in that case, we say that this condition or this rule is true. We say that it is vacuously true. Okay, so if you are not in the classroom, then obviously you are not a rule breaker, because this rule doesn't even apply to you. So in that case, we say that this rule this rule is vacuously true, or it holds vacuously. So when does it fail? It fails only when you are in the classroom and then you eat. So in that case, it fails. Alright? So what we first must look at is this if statement. If you are in the classroom. So if this doesn't happen, then this second one need not happen. Right? If you're not in the classroom, then you don't even have to, you may eat, you may not eat. You are never a rule breaker. Right? So let's use this analogy here. If AB and BC belong to R, then AC belongs to R. Now, take a look at this relation here. can you find such AB and BC? So let me write this again here. So 1 1, 2 2, 3 3. Can you find such AB and BC? So we say that, okay, suppose we take this as AB, then what will be BC? So there's none, right? There's none. Or we may say that, okay, let's take the same element as BC. So we could do that possibly, but then in that case AC will also be 1 1, right? So what if you take this 2 2 then as AB? Then can you find BC? No, because there's no other element that this ends with 2. So B, there's no other element here or the pair that starts with 2. So you cannot find that BC, right? So you can get the AB, but you cannot get the BC. So that means this if condition doesn't hold. It's not true. That means you don't even need to check this second condition here. Just like in this case, if you're not in the classroom, you don't even have to check whether you're eating or not. You're never breaking that rule, right? So in this case, because BC is not there, the if statement fails. So this condition for transitivity will hold vacuously, or we say that this R is vacuously transitive, or we can say that the condition for transitivity is vacuously true. Okay, so let me just write this. The condition for transitivity of R is vacuously true. So R is transitive. So R is transitive now. It is also reflexive. It is also symmetric. So hence R is an equivalence relation. And we have our answer for that number 4. Question 4. So that's true. Then finally, the universal relation on A is an equivalence relation. The universal relation is the relation, okay, let me show you. If I have A equals 1 to 3, then the universal relation is the relation that contains all elements, all the possible elements. Suppose I have the set here A. So 1, 2, 3, and it's a set from A to A. 1, 2, 3. So 1 relates to 1, 1 relates to 2, 1 relates to 3, 2 to 1, 2 to 2, 2 to 3, 3 to 1, 3 to 2, 3 to 3. So all elements. So 1, 1, 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3. In other words, what is this? This is simply the relation A cross B, the Cartesian product A cross B. Okay, so the question now is this relation an equivalence relation? Okay, we just write all of this. So we've reached 2, 3, then even 3, 1, 3, 2, 3, 3. Okay, so is this reflexive? Yes. You have 1, 1, you have 2, 2, and you have 3, 3. So all for each of these elements, 1, 2, 3, we have their AAs, their 1, 1, 2, 2, 3, 3's. So R is definitely reflexive. It's symmetric now. So if we pick this as AB 1, 2, we also see the BA here 2, 1. Then if we look at this 1, 3, then we have the 3, 1 also there. If you look at 2, 3, then we also have 3, 2. So nowhere does it fail the condition for symmetric. So we have this one. So the relation R is symmetric. Then finally, let's look at transitive. Is it transitive? If we pick AB, pick 1, 2, AB, then what will work as BC? So something starting with 2, because it ends with 2. We take this one, BC. Then in that case, AC will be 1, 1. So 1, 1 is there. Okay. So if we take this AB 1, 2, then we might take this one as BC 1, 2, 2, 3. So what is AC? AC is 1, 3. 1, 3 is there. Yes, yep, it's here. You can check all these possibilities and you'll find nowhere does the condition for transitivity fail, right? So this will be transitive, of course, right, because it has all the possible elements. So nowhere will it not have an element that you need. Okay, so this will be transitive, and hence it's all the three, so it is an equivalent solution. So that's it for the true or false question. So this is true.